For this first problem, we're asked to compute M3, the midpoint approximation for this integral. So we're going to take that interval from 1 to 7 and break it up into 3 equal pieces. So our delta x is going to be b minus a over n, as it always is. In this case, that's 7 minus 1 divided by 3, which works out to be 2. And so that means that our dividing lines are 2 units away from each other. So our intervals are 1 to 3, 3 to 5, and 5 to 7. Since we're using the midpoint rule, we want the number that's halfway in between each of these guys. So that's 2, 4, and 6. And so our midpoint approximation, M3, is going to be delta x times the sum of f of each of those numbers. So f of 2 plus f of 4 plus f of 6. So my delta x is going to be 2. F of 2 is going to be cosine of 4, whatever that works out to be in our calculators, plus cosine of 16 plus cosine of 36. And when we punch all those numbers in our calculator, what we get is negative 3.4785. So now we're in the process of trying to approximate this integral accurately. So what we want to do is find that value of k so that the size of our second derivative is always less than or equal to k for the interval that we're looking at between 1 and 7. So we need to plot the second derivative, which means we need to find the second derivative. So our f of x is cosine of x squared. So what's the second derivative of that? Well, we find the first derivative. So f prime of x is going to be, using the chain rule, negative sine of x squared times 2x times the derivative of the function inside. So for my second derivative, I'm going to need to use the product rule and the chain rule. So the product rule tells me that it's the derivative of the first function. The derivative of the first function is minus cosine of x squared times 2x, that's the chain rule again, times the second function. So this was the derivative of the first function, times the second function, and then plus the first function, negative sine of x squared, times the derivative of the second function, which is 2. So that's our f double prime. Now we could simplify that, or we could just type it into our calculator as is, and when we do that and graph it on the interval from 1 to 7, this is the picture we end up with. Now on our calculator we have to tinker around a little bit. We have to use some trial and error to find a good y range. This y range that I have posted here is from negative 200, that's this low y value here is minus 200, up to positive 200 up here. So that means that the k value I want to use is 200. So now that we've got that value of k, we want to use our error-bound formula to figure out what value of n would make this integral approximation be as good as we'd like it to be. So in this case we want accuracy to 2 decimal places. So we know that E sub m, the error in the midpoint approximation, is less than or equal to this k times b minus a divided by 24 times delta x squared. Now, since we're looking for n, I'm going to write delta x as b minus a over n, and that's being squared. And since I want my accuracy to be within 2 decimal places, that means I want my error to be less than 0.005. So let's plug in what we know. We know k is 200, we know b is 7, we know a is 1, 24 is 24, b is 7, a is 1, n is this unknown thing that we're looking for, and now we just have an inequality that we have to solve. 200 times 7 minus 1 over 24, that simplifies down to be 50. 7 minus 1 is 6, so 6 squared is 36 over n squared. And we've still got the 0.0005 over here. And so now when we want to solve for n, we're going to multiply both sides by n squared. 50 times 36 is 1800, so we get 1800 less than 0.005 n squared. Divide both sides by 0.005. 1800 divided by 0.005 works out to be 360,000. And then we take the square root of both sides, and the square root of 360,000 works out to be 600. So that means that for us to get this accuracy that we're looking for, we need to use more than 600 rectangles. So n greater than 600, that would be our solution. For this next problem, we're asked to solve an initial value problem, y prime equals 2x y squared and y of 1 equals 3. So we'll focus on the differential equation first. So first of all, we need to separate the variables. Just for convenience sake, I'm going to rewrite y prime as dy dx. I'm going to leave the 2x on the right-hand side, but I'm going to move the y squared over to the left-hand side by dividing both sides by y squared. So now I'm going to integrate both sides. The integral of 1 over y dy dx with respect to x is equal to the integral of 2x with respect to x. Of course, on the right-hand side, that's just x squared plus c. That's not too bad. On the left-hand side, again, we sort of think of this substitution rule thing. We think of the dx's as canceling, even though that's not really quite what's happening. It's really just the substitution rule, but we end up with the integral of 1 over y squared dy. Now be careful here, you're going to be tempted to think that this integral works out to be some sort of natural log, but of course it doesn't. When we think of this integral, we want to think of this as y to the minus 2, and when we integrate y to the minus 2, we get minus y to the minus 1 equals x squared plus c. So now y to the minus 1, that's 1 over y, so this is minus 1 over y equals x squared plus c. If we want to solve that for y, let's flip over both sides, so we get negative y equals 1 over x squared plus c. Notice that that plus c is in the denominator because we flipped over the right-hand side. So you don't just have the plus c hanging off the end. And then we just multiply both sides by minus 1, and we get y equals negative 1 divided by x squared plus c. Now, if this were not an initial value problem, we'd be done. But since it is an initial value problem, we've got to go back and plug in y of 1 equals 3. So we substitute 1 in for x and 3 in for y and solve for the c. So we get 3 equals negative 1 over 1 squared is 1 plus c. Multiply both sides by 1 plus c, we get 3 plus 3c equals negative 1. 3c equals negative 4, so c equals minus 4/3. So our final answer is y equals negative 1 divided by x squared minus 4/3. For this problem, we've got an integral x times the sine of x. Now when we look at that, we see two functions multiplied together, so we think to ourselves, maybe integration by parts is what we want to use here. And it turns out we're right. And remember, with integration by parts, we've got to figure out what should u be and what should dv be. And we want u to be something that gets nicer when we take its derivative, and we want dv to be something that doesn't get too much nastier when we take its antiderivative. So the natural choice here is to let u equal x and dv equal the sine of x. So that means that my du is simply 1 dx, and my v is the antiderivative of sine, which is negative cosine. So that means that my integral, x sine x, is equal to uv, so x times negative cosine of x, minus the integral of v du, which is going to be negative cosine of x, times 1 dx. So this is minus x cosine x. Minus and minus is a plus. And the integral of cosine is sine. And we're done. In this problem, we've got a power of sine times a power of cosine. Remember, in these kinds of problems, what we're looking for is an odd power. And good news, we have an odd power right here. The power on sine is sine cubed. So that means that what we want to do is hold aside one copy of sine. So way down here next to the dx, I want to have sine of x. That's going to make the substitution that I'm going to do in a little bit work well for me. And then I want to turn everything else into cosines. Well, I already had a cosine squared, so I'm going to leave that alone. And then the sine cubed here, I took away one of the powers of sine, so what I have left is sine squared, How do I rewrite sine squared in terms of cosine? Well, sine squared is 1 minus cosine squared. And the substitution that I want to do here is u equals the cosine of x. And when I do that substitution, my du is negative sine of x. And that's the reason why I wanted to have this one copy of sine here. Now I've got negative sine of x, so that means that I'm going to stick in here a negative 1, and then that means I have to put a negative 1 out front. So what I end up with is negative 1 integral. U was cosine of x, so this is 1 minus u squared times u squared. And then all this business here, the minus 1 times the sine of x dx, that's my du. So if I multiply that out, I get negative 1 u squared minus u to the 4th du. Now I can take my antiderivative, so I get negative u cubed over 3, minus a minus is a plus, u to the 5th over 5, plus c. And of course we're not quite done because we need to go back to the original variable. U was the cosine of x, so this is negative cosine cubed over 3, plus cosine to the 5th over 5, plus c. And now we're done. Finally, for this integral, we've got 4 divided by x cubed plus x, which might not be obvious how to approach this, but if we think about this, we can factor that denominator, x cubed plus x, is really just equal to x times x squared plus 1. And if we do that, that might lead us to believe that maybe what we should do here is partial fractions. So when we think about it that way, we've got 4 divided by x times x squared plus 1. And we know from partial fractions that's going to break up as a over x plus b over x squared plus 1. Sorry, bx plus c over x squared plus 1. That x squared plus 1 is an irreducible quadratic factor, so the top has to be linear. So we're going to multiply both sides by x times x squared plus 1. When we do that, we get 4 equals a times x squared plus 1 plus bx plus c times x. Now we can plug in x equals 0 here, and if we do that, we're going to figure out the value of a. So on the left-hand side we get 4, a times 0 squared plus 1 is 1, and then bx plus c, whatever that works out to be, but x is 0, so multiply that by 0, you get a 0, and that tells us that a equals 4. Or what about b and c? Well, for that we're going to have to multiply this out and equate coefficients. So we do that over here. We're going to get 4 equals, we know a is 4, so 4x squared plus 4. We don't know what b and c are, but when I take this bx times x, I get bx squared. And when I take the c times the x, I end up with cx. So now, equating the coefficients on the left-hand side and the right-hand side, I get 4 equals, I have 4 plus b times x squared. I've got cx, and then I've got 4. So on the left-hand side, I don't have any x squareds, which means that 4 plus b has to be 0. That means b has to be negative 4. And on the left-hand side, I don't have any x's, which means that c has to be 0, because the coefficients on the left have to equal the coefficients on the right. So now I'm ready to actually go back and do my integral. What I figured out now is that the integral that I started with, 4 divided by x cubed plus 3x, is equal to the integral of a over x, so that's 4 over x, plus the integral of bx plus c over x squared plus 1. Well, let's see, b was just negative 4, so negative 4x, and c was 0, so just have negative 4x divided by x squared plus 1. Okay, so 4 over x, what's the antiderivative of that? Well, you can think of that as 4 times 1 over x, and the antiderivative of 1 over x is natural log of the absolute value of x. What about over in the second interval, negative 4x divided by x squared plus 1? Well, if I do a substitution, u equals x squared plus 1, my du is going to be 2x. Now I have a negative 4, so what I can do is break that negative 4 up into 2 times 2, or minus 2 times 2 I should say. Pull out the negative 2, and that gives me what I want. So I've got plus 2 times negative 2 times the integral of 2x divided by x squared plus 1. So now when I do my substitution, I get 1 divided by u du. Almost done. And so I get 4 times the natural log of the absolute value of x minus 2 times the natural log of u, but u is x squared plus 1. And so we're done. Now for this problem, we want to find the area of a region bounded by two curves. So the best way to get started with this is to actually draw a graph of these two curves. And our calculator is pretty helpful for this. When we throw this on our calculator, we get a graph that looks a little something like this. There's our line, and then a parabola looks something like that. So the area that we're looking for is this area in here, in between the line and the parabola. So we know that our integral is going to look like the top curve minus the bottom curve, and now that we've got our picture, we can see that the top curve is going to be 8x minus 10, and the bottom curve is going to be the parabola x squared minus 4x plus 10. So the only thing that we don't know are these two bounds. What number goes there, and what number goes there? And to do that, we need to figure out when these two curves are equal to each other. So we need to solve the equation 8x minus 10 equals x squared minus 4x plus 10. But that's an easy quadratic equation. So we get 0 equals x squared minus 12x. Add 10 to both sides, plus 20. So we're looking for two numbers that multiply together to be positive 20, but add together to be negative 12. It doesn't take us too long to figure out that we need negative 10 and negative 2. Which means our two roots are at x equals negative 2, or sorry, positive 2, so this is 2 comma something, and this point up here is 10 comma something. And again, we could work hard to figure out what those y values are, but we don't need them in this problem, so let's just leave those blank. So now we know that the bounds on our integral are 2 to 10. Okay, so now we're ready to take our antiderivative and plug in. So first let's simplify our integrand. That's going to make our life a little bit easier as we go on. When I subtract 8x minus 10 minus x squared minus 4x plus 10, I get negative x squared plus 12x minus 20. Let's go ahead and take our antiderivative. Negative x cubed over 3 plus 6x squared minus 20x. Now I've got to plug in 10 and plug in 2 and subtract. Alright, plugging in 10, we get negative 1,000. 10 cubed is 1,000. Plus 600. Minus 200. And then minus what we get when we plug in 2 is negative 8 over 3. Plus 2 squared is 4, 6 times 4 is 24. And then 20 times 2 is 40. And when we throw all that stuff on our calculator and simplify, we end up with 256 over 3. And that's our answer. Now for this problem, we want to convert from polar coordinates to rectangular coordinates. Remember that this is the easier direction because there's no ambiguity. X is just equal to r cosine theta, and y is equal to r sine theta. So that means that x is going to be 4 times the cosine of 3 pi over 2, and y is going to equal 4 times the sine of 3 pi over 2. The cosine of 3 pi over 2 works out to be 0, and the sine of 3 pi over 2 works out to be negative 4, and so the coordinates we're looking for are 0, negative 4. Now in this next problem, we have to convert from rectangular coordinates to polar coordinates, and here there are going to be many possible correct answers. So first let's draw ourselves a little picture so that we know where in general this point is. So we've got negative radical 3 comma 1, that's going to be over here somewhere. So that's where my point negative square root of 3 comma 1 is going to be. So one of the things I'm going to have to figure out is that angle theta. And the other thing I'm going to have to figure out is my distance r. So what we know is that our relationship is that r squared equals x squared plus y squared, and that the tangent of this angle theta is going to equal y over x. So using our r squared formula first, we know that r squared is going to be x, which is negative radical 3 squared, plus 1 squared. That works out to be 4. And so that means that my r is either going to be plus or minus 2. And again, you're going to be tempted here to just take the square root and say that r equals 2. But we'll see in a second why that might not be the right plan. Now we're going to use our tangent and say, okay, that the tangent of theta is going to be positive 1, the y value, divided by minus the square root of 3. In other words, minus radical 3 over 3. And again, if we're thinking about what that what that theta is, we might just want to plug negative radical 3 over 3 into our inverse tan function. But here's where we realize that we might be doing something wrong if we just do the, not thinking approach of just saying that r equals 2 and tan theta, or that theta equals the inverse tan of minus radical 3 over 3. As I talked about in class, when we plug something into the inverse tan function, the angles that we get are always between minus 90 and 90. And that's because that as theta goes from 0 to 2 pi, tangent takes on the same values twice. So the values that it takes on in quadrant 1, it takes on those values again here in quadrant 3. And the values that it takes on in quadrant 2, it takes on those values again here in quadrant 4. So our angle is in quadrant 2. And if we plug this number, negative radical 3 over 3, if we plug that into the inverse tan function, we're going to get an angle here in quadrant 4. We're going to get this angle here. Now, that might be okay. We might be okay with that angle. But if we do that angle, then we need to use a negative value of r to get this point that we're looking for. So one possibility would be to say that the point we're looking for has polar coordinates negative 2, comma, the inverse tan of minus radical 3 over 3, which would be negative 2, comma, negative pi over 6. Again, just using some knowledge of trig there. But another idea that we could do, another option, is to use the positive value of r, but then think about what that angle would actually be. Again, we're thinking about which angle in quadrant 2 is this. Well, if the angle that we got in quadrant 4, if this angle here was minus pi over 6, that means that the angle in quadrant 2 that we're looking for would be 5 pi over 6. Again, just thinking about some trigonometry there. So this is a possible solution, totally correct, and this is another possible solution, also totally correct. For this problem, we've got a parametric curve, and we want to find the slope of the tangent line. And again, remembering from class, we know that dy dx is going to equal dy dt, the derivative of the y function, divided by dx dt, the derivative of the x function. So in this case, that's 3 squared plus 1, divided by 2t. And if we want the tangent line at t equals 3, all we have to do is plug in t equals 3. On the top, 3 times 3 squared is 27, plus 1 is 28. And at the bottom, 2 times 3 is 6. So 28 over 6 is the number we're looking for. For this one, we've got a power series, and we're asked to compute the fourth derivative of this function evaluated at 0. So one option we have is to start taking derivatives and take 4 derivatives and then plug in 0. But actually we don't have to work nearly that hard. There's actually a trick to this question, which is that this x to the 4th term is the term that tells us what the 4th derivative is going to be. The coefficient of x to the 4th is the 4th derivative of f evaluated at the center of the series, which in this case is 0, divided by 4 factorial. And that f 4th derivative evaluated at 0, that's the number we're looking for. But we also know what this coefficient is. It's 1 divided by 2 cubed times 3 factorial. So that means that my 4th derivative evaluated at 0, all I have to do is multiply both sides by 4 factorial. And I can simplify this. 4 factorial divided by 3 factorial is just 4. And then 2 cubed is 8, so this 4 is going to divide out with that 8, leaving a 2 on the bottom. And so this equals simply 1/2. And that's it. Hopefully you believe that that's easier than taking 4 derivatives and trying to plug in 0 and see what we get. For the next one, now we're looking for the interval and radius of convergence of this series. So again, the series, it's on the previous slide, so just to rewrite it here for you, was k goes from 0 to infinity of x to the k plus 1 divided by 2 to the k times k factorial. Now remember that when we're doing interval and radius of convergence, we can usually either use the ratio test or the root test, but in this case we see a factorial, so we really shouldn't use the root test, we should use the ratio test. That's going to work out much better for us. So in the ratio test, we're going to look at the limit as k goes to infinity, and we're going to have the absolute value of the k plus first term divided by the kth term. Now the kth term is easy, the bottom is always just what you see there in the series, so x to the k plus 1, 2 to the k times k factorial. And then on the top, this is just when k equals, or when we have k plus 1, so we have k plus 1 plus 1. So we have k plus 1 plus 1 divided by 2 to the k plus 1 times k plus 1 factorial. There we go. And so now we're going to try to simplify that, because we want to try to think about what happens to this thing as k goes to infinity. So we've got a fraction over fraction, so we're going to flip over the bottom fraction and multiply. So we've got x to the k plus 2 divided by 2 to the k plus 1 times k plus 1 factorial. And then we flipped over the bottom fraction, so we get 2 to the k on the top, k factorial, divided by x to the k plus 1. Alright, now we start simplifying like crazy. X to the k plus 2, x to the k plus 1, we're going to get an x left over on the top. 2 to the k plus 1, we get a 2 on the bottom. K factorial, k plus 1, we get a k plus 1. And so after all the smoke clears, we get limit as k goes to infinity of x divided by 2k plus 2. Absolute value. Now what happens as k goes to infinity? Well, x isn't going anywhere. X is just whatever number we decided to try to plug into this power series to see if it converged or not. But k is going to infinity. So no matter how big or small x is, this k plus 2k plus 2 here on the bottom is going to get bigger and bigger and bigger and bigger. And so this fraction is going to go to 0. And it doesn't matter what x is, that's going to go to 0. Now we were using the ratio test, so what's important about that number 0 here is that it's less than 1. And since 0 is less than 1, that means this series converges for all x. And that means that my interval of convergence is minus infinity to infinity, and that my radius is infinity. And in this case, this is convenient because I don't actually have any endpoints to check. Normally, if we get a real interval, like from 3 to 7 or something like that, we'd have to check the endpoints specifically. But in this case, we don't, because we know that this series converges for all values of x. So now we want to approximate f of negative 0.1, and we're given an error tolerance of less than 0.00001. So the hint here is to think about what kind of series f of minus 0.01 is. So let's write it out. Let's write out what f of minus 0.1 is. Well, that's going to be the sum, as k goes from 0 to infinity, of negative 0.1 to the k plus 1, divided by 2k, 2 to the k, divided by k factorial. And so if we start writing out what these terms look like, we've got negative 0.1, and then plus 0.01, or 0.1 squared, negative 0.1 squared, divided by 2 squared times 2 factorial, plus negative 0.1 cubed divided by 2 cubed times 3 factorial, and so on. And what we might notice here is this is actually an alternating series. That's what I mean when I say what kind of series is f of minus 0.1. It's alternating. And that means that if we want to approximate the sum of this series, then all we have to do is find a term of this series that's less than the error tolerance that we want. We need to keep looking at the terms of this series until we find one that's less than 0.00001. And then when we do, all we have to do is add up all the terms that came before that one, and then that'll give us the sum that approximates our series. So it's probably not going to be one of the first couple of terms, but maybe it's this third one that we tried. Maybe it's 0.1 cubed times 2 cubed, divided by 2 cubed times 3 factorial. So let's try that. So negative 0.1 cubed divided by 2 cubed times 3 factorial. And when we type that in our calculator, we get about 2.08 times 10 to the minus 5, which is 0.00002. So not quite small enough, but if we go to the next term, pretty safe bet that that's going to be small enough. So negative 0.01 to the fourth divided by 2 to the fourth times 4 factorial. And our calculator tells us that that's about 2.6 times 10 to the minus 7, which is definitely small enough. That's definitely less than 0.00001. And so that means that the way to approximate our series with this degree of accuracy is to simply add up these first three terms. So we're going to take these first three terms and add those up and see what we get. So we've got negative 0.1, negative 0.01 squared divided by 2 squared times 2 factorial, and then negative 0.1 cubed divided by 2 cubed times 3 factorial. And again, all we're doing is we're going to type those in our calculator and add them all up and see what we get. And when we do all that, we get negative 0.09877. And that's our answer. Now for this last question, we want to try to identify this function in terms of our well-known elementary functions. So we've got the sum, k goes from 0 to infinity, of x to the k plus 1 divided by 2 to the k times k factorial. So when we see that x to the k plus 1 on the top and the 2 to the k on the bottom, we'd like to combine those into one exponential term. But the problem is that the exponents are different. And so one way that we can fix that is by rewriting this so that we pull out an x. So we write this as k equals 0 to infinity of x times x to the k. Again, think of that as x to the first times x to the k. So that's x to the k plus 1. And then 2 to the k, k factorial. So I'm going to do two things at once here. I'm going to factor out the x from the sum, so in other words, pull it outside of the sum. And then I'm going to rewrite my x to the k divided by 2 to the k as simply x over 2 to the k divided by k factorial. And now at this stage, all we have to do is remember some of those well-known series that we talked about. So one of those well-known series is that the sum of x to the k divided by k factorial, k going from 0 to infinity, is our good old friend e to the x. And so that's almost exactly what we have here, except we just have x over 2 to the k instead of x to the k. And so that means that what this function really is e to the x over 2. And we've identified our function, and we're done. Alright, now we've got some series that we want to analyze. So here we've got 2 to the 2k plus 1 divided by 5 to the k. So if we want to try to figure out if the series converges or diverges, then a couple different things we could do here. We could use the ratio test, since we see some exponential things. We could use the root test, but probably the easiest thing to do is to recognize that the series is actually geometric. If we start writing out some terms of this, when k equals 0, we just get 2 to the first divided by 5 to the 0. When k equals 1, we get 2 cubed divided by 5 to the first, 2 to the fifth divided by 5 squared, 2 to the seventh divided by 5 cubed, and so on and so on. And what we might notice is that from each term to the next, what we're doing is multiplying by 4/5, or 2 squared over 5, multiplied by 4/5, and so on. And so that means that this series is geometric with my common ratio being 4/5. 4/5 is less than 1, so the series converges. And in fact, we could figure out what this series converges to. We could actually add it up, but we weren't asked to do that, so we don't have to. If we did, it would be a over 1 minus r, and then we just plug in our numbers. For this next series, we've got k over k squared minus 1. And again, what we think about here is that the minus 1 on the bottom doesn't really matter. So this is pretty much just like the sum of k over k squared, which is the sum of 1 over k. And that's our good old friend the harmonic series, which we know diverges. So our guess is that this series probably diverges also. And what we're really trying to do here is a comparison. So let's see if the comparison works. We've got k over k squared minus 1. How does that compare to k over k squared? Well, this fraction has a smaller denominator, because I'm subtracting 1. And it's got the same numerator, so when you have a smaller denominator, that means you have a bigger fraction. And so k over k squared minus 1 is bigger than k over k squared. And k over k squared is the one we know. That's 1 over k, which we know diverges. And so our series is bigger than a divergent series. That's the direction we want the inequality to go, so our comparison test is going to work. So comparison test says that since the series 1 over k diverges, and we know that because it's a harmonic series, then the series that we have, the sum of k over k squared minus 1, must also diverge. And that's it. Next up, we've got k squared over 3k squared plus 10. Again, if we think about this the way we thought about the previous problem, thinking about the fact that the plus 10 doesn't really matter, then this time, this series looks like the sum of k squared over 3k squared, which is just the sum of 1/3. So that would be 1/3 plus 1/3 plus 1/3 plus 1/3, but that's not going to converge, that's going to diverge. And in fact, the limit, as k goes to infinity, of the terms of my series, k squared over 3k squared plus 10, either by L'Hopital's rule or dividing top and bottom by k squared. Let's divide top and bottom by k squared. So when we do that, we get the limit as k goes to infinity. On the top I just have 1, on the bottom I have 3 plus 10 over k squared. 10 over k squared, that's going to go to 0. And so in the limit, I'm going to get 1/3. And 1/3 is not 0, which means this series cannot converge. It must diverge by the test for divergence. And again, in a problem like this, your intuition might tell you, hey, those numbers are getting closer to 1/3, and so that means this series diverges by the test for divergence. But you really do need to show this work. You need to explain how you know that the limit really does equal 1/3. Your intuition isn't quite good enough. So the test for divergence. All right, last problem. So now we're talking about a region bounded by two curves, y equals 2 times the square root of x and y equals x. So again, if we're talking about trying to slice this thing and spin it around to get volumes, the best thing we can do for ourselves is get ourselves a good picture. So y equals 2 times the square root of x is going to look like that. And then y equals x is going to look like this. And so the region that we're talking about is this region here, in between these two curves. It's going to be helpful for us to find this intersection point. So let's go ahead and set these two curves equal to each other. X equals 2 radical x. Let's square both sides. X squared equals 4x. Subtract x from both sides, 4x from both sides, and we get x equals 0, x equals 4. So this point here is 4 comma something, but since one of the curves is y equals x, it's not too hard to figure out that the y-coordinate is also 4. Okay. So in this first question, we want to rotate this volume about the x-axis and find the volume obtained. So since we're rotating about the x-axis, the easiest thing to do is to slice this region vertically and get these vertical rectangles. And when we spin it around the x-axis, we're going to get washers. So it doesn't hurt to write down the word washer so that on the exam I know what you're talking about. And our volume here is going to be pi times, since we're integrating with respect to x, our x value is going to go from 0 to 4, and it's going to be the outer radius squared minus the inner radius squared. Well, the outer radius is going to be based on the top of our rectangle. That's the part that's furthest away from our axis of rotation. So this top rotating around, that's going to give us our big circle. And so that's going to be 2 radical x squared minus our inner radius, that's based on the bottom of our rectangle. And our bottom of our rectangle is y equals x, so that'll just be x squared. And we're asked to set up but not evaluate the integral, so that's all we have to do. And finally, for our last problem, we want to find the volume obtained when this region is revolved around the line x equals minus 2. So again, we've got our same picture from before. Let me just recreate it here for you real quick. So there's my square root function, there's my y equals x, here's the point 4, 4, and x equals minus 2 is a vertical line over here. And again, since we're rotating about a vertical line, the easiest thing to do would be to slice this curve horizontally. Sometimes that works, sometimes it doesn't, but it will work for us here. And that means that we're integrating with respect to y. So our volume is going to be an integral. Our y values go from 0 to 4. And when we've got a washer again, we're going to have pi times the outer radius squared minus the inner radius squared. So the outer radius is based on the right-hand end of this rectangle, and it's the distance from the right-hand end of the rectangle to the axis of rotation. So the outer radius is going to be this distance here, from the outer end of the rectangle down to here, down to x equals negative 2, which is what that vertical line is. So this right end of the rectangle, this part right here that I'm highlighting with the laser pointer, is x equals y, and so it's going to be the distance from x equals y to x equals negative 2, which is going to be y minus negative 2. That's how far apart those two numbers are. And that's my outer radius, so I square that, minus the inner radius. Well, the inner radius is going to be the distance from the left end of the rectangle to my axis of rotation. And the left end of my rectangle is, well, let's see, I've got it as y equals 2 radical x. But since I'm integrating with respect to y, I've got to solve that for x. So let's square both sides. Y squared equals 4x. X equals y squared over 4. And so that means that my inner radius is going to be y squared over 4 minus negative 2. That's my inner radius, square that, and then integrate with respect to y. And again, we were asked to just set up and not evaluate the integral, so that's what we're looking for.